Hello everyone. Welcome to First Online University, a global platform for all your education and growth related needs. In this lecture, we are going to continue with the chapter P block elements, and we are going to discuss group 14 elements and their chemical properties. We've already covered the introduction and physical properties of group 14 elements. In this particular lecture, we'll be taking up the chemical properties. Before we begin, a piece of information for you. You can use the coupon codes Mission J or Mission NEET while you enroll at First Online University for Mission J or NEET in order to avail good discounts. Let us begin with the part 1 of chemical properties of group 4A elements. Now, the first chemical property that we are going to discuss is the oxidation state and the trends in chemical reactivity that we observe. Now, what are the two oxidation states that group 13 elements could show? It was +1 and +3 because they had the electronic configuration Ns2Np1. So, one electron when removed from the p subshell gave a +1 oxidation state possibility, and when one from P and 2 from S could be removed, it gave a +3 oxidation state possibility. But when we talk about group 14 elements, we have Ns2Np2. So there are two possible oxidation states that can be shown, +2 and +4. That is removal of 2 electrons from the p subshell and further removal of 2 electrons from the s subshell would give +4 oxidation state. So let us see how this affects the chemical reactivity. So their common oxidation states are +2 and +4. Their valence shell contain 4 electrons so that the maximum possible oxidation state is +4. The lower members in the group are going to show +2 oxidation state because it becomes more stable due to inert pair effect. Carbon has both +4 and -4 stable oxidation states. Silicon and germanium will have +4 oxidation state. Tin and lead will have stable +2 oxidation state. So you have to remember the stable oxidation states of each of these elements. Now, because of the absence of d orbitals, in carbon we do not have any d orbital present, and therefore it cannot expand its covalency beyond 4. Rest of the elements can exhibit a covalency up to 6. The stability of the +4 oxidation state is going to decrease down the group. That is, germanium 4 plus is more stable than tin 4 plus, which is further more stable than lead 4 plus. The stability of +2 oxidation state will increase down the group, and therefore lead 2 plus will be more stable than tin 2 plus, which will be more stable than germanium 2 plus. Lead 4 plus is less stable and thus it will act as an oxidizing agent. Itself gets reduced from +4 to +2 oxidation state. So something which is itself getting reduced will oxidize the other species and therefore will act as an oxidizing agent. Now, if we look at this table, the element, its metallic nature, color and oxidation states are given to you. So this table in short, okay, in brief is giving you a lot of important information here. So when we talk about carbon, it is a non-metal. It is black in color and its stable oxidation states are +4 and -4 also, okay? Then for silicon, which has atomic number 14, it's a non-metal, light brown in color and stable oxidation state is +4. For germanium, atomic number 32, it is a metalloid, which is grayish-white in color. +4 and +2 are the stable oxidation states. Then tin, having atomic number 50, is a metal, having a silvery white color, and +4, +2 are the stable oxidation states. For lead, atomic number 82, which is a soft metal, which is again silvery white in color, has +2 and +4 as stable oxidation states, +2 being more stable. Next, we talk about the reactivity towards oxygen now. So they form two types of oxides with oxygen, monooxides. That is when metal is going to react with oxygen to form in a limited amount to form MO on heating. That is monooxide. Okay, and when M is any group 14 element. The second possibility is the formation of dioxides. That is when metal is going to react with oxygen in excess. On heating will form MO2. That is, again, M could be any group 14 element and a dioxide is going to be formed. For example, if you look at the example of monoxide, carbon monoxide, germanium monoxide, tin oxide, lead oxide, these are all monoxides. with CO being neutral, GeO being acidic, tin and lead oxides being amphoteric in nature. So silicon oxide is the only one that exists at high temperatures and it is weakly acidic. Then we talk about dioxides, carbon dioxide, silicon dioxide, germanium dioxide, tin dioxide, and lead dioxide. Carbon, silicon, and germanium dioxides are weakly acidic in nature. Tin and lead dioxides are amphoteric. So for tin and lead, both the oxides and monoxides and dioxides are amphoteric in nature. And for germanium and silicon, both monoxides and dioxides are weakly acidic. For carbon monoxide, that is neutral, and carbon dioxide is weakly acidic. This is how you can remember. Let's do a few MCQs based on this. Carbon cannot exceed a covalency of 4 because of the presence of d orbital, absence of d orbital, presence of p or absence of p orbital. It is always associated with the d orbital, first of all, whether a particular element can or cannot expand its covalency. So if the d orbital is absent, it will not be able to expand its covalency. Therefore, absence of d orbital, that is option B, is the correct answer. Next question is, the element which shows stable +2 oxidation state is carbon, germanium, tin or lead. We know down the group the lower oxidation state, that is +2, is going to become more stable because of inert pair effect. Therefore, lead, option D, is the correct answer. Next question is, which group 14 element forms most acidic dioxide? Most acidic dioxide, carbon, germanium, tin or lead. We have seen that it is carbon which is going to form the most acidic dioxide. We have already discussed this part. Now we move on to part 2 of the chemical properties of group 14 elements. Here we are going to talk about the reactivity towards water. So in group 14 elements, it is only tin which is capable of reacting with boiling water to form dioxide, and H2 gas is going to be liberated. So tin will react with H2O, that is HOH is how we represent it. On heating, will get converted into SnO2, that is tin dioxide, along with H2 being liberated. And this is how we can balance the equation. So stannum is going to react with water to form stannic oxide and dihydrogen. Note that lead is not affected by water because an oxide film is going to be formed on the surface of lead, which will prevent its reaction with water. Next is reactivity towards halogen. These elements can form two types of halides, MX2 and MX4, with an exception of just carbon. Carbon and silicon do not form stable dihalides. Now, for example, let us take a general equation where metal is going to react with X2 to form, in a limited amount, on heating, it will form MX2, that is dihalide, and when it is going to react with X2 in excess, on heating will form MX4, which is tetrahalide. Okay, so we can see that heavier members, that is from germanium, tin, lead, they form MX2 because they show +2 oxidation state, more than +4 oxidation state, and most of the MX4 are covalent in nature, but tin tetrafluoride and lead tetrafluoride are ionic in nature, whereas lead iodide, that is PbI4, does not exist. Okay, these are few facts that you will have to remember. In MX4, the hybridization of the central atom is sp3 and the molecular shape is going to be tetrahedral, not square planar. Now, tetrachlorides are easily hydrolyzed by water due to the presence of d orbitals, but CCl4, that is carbon tetrachloride, since carbon does not have a d orbital, it cannot be hydrolyzed. Next fact here is that the central atom can accommodate the lone pair of electrons from oxygen atom of water in the d orbitals. Okay, for the atoms, for the elements which have d orbitals. So when we talk about hydrolysis, that can be understood by taking the example of SiCl4. So if I take silicon tetrachloride as the example, SiCl4 on reaction with water is going to have HCl getting removed. So one chlorine from SiCl4 and one hydrogen from water are going to get removed as HCl, and we will have one OH introduced on SiCl4. In place of one Cl, we will have OH being formed. So SiCl3OH is going to be formed, and now in the similar way, each of the three chlorine atoms are also going to be removed as HCl, and now we have SiOH whole 4. So this is how we will have the hydrolysis of SiCl4 taking place. SiF6 2 minus is known, but SiCl6 2 minus does not exist. Why? The answer to this is that the chlorine atoms are larger in size as compared to fluorine atoms, and 6 large chlorine atoms cannot be accommodated around Si4 plus, which is small in size and has this limitation because of its small size. Then also the interaction between the lone pairs of chloride ions and Si4 plus is not very strong, as there is the interaction between F minus ion and Si4 plus ion. Let's have a look at few MCQs now. Why lead is not affected by water? Because it forms a protective chloride layer, protective oxide layer, both A and B, or none. So it forms a protective oxide layer. Option B is the correct answer. Next question is, which of the following will not undergo hydrolysis? We have seen that all of them can undergo hydrolysis except CCl4 because it does not have a vacant d orbital. So option C is the correct answer. So this is all about the chemical properties of group 14 elements that we had to discuss. You need to keep revising alongside, and please write all the equations by your hand so that you are well versed with these equations and reactions. You can subscribe to our YouTube channel for joining YouTube live classes for best NEET or JEE coaching. You can also download the First Online University mobile app through Google Play Store or App Store for continuous learning through your smartphones. Keep learning with First Online University, a team of millions of learners and educators worldwide.